Lecture 5, Damped Harmonic Motion. This is the first of two lectures on the chapter Damped Harmonic Motion, in which we will introduce the motion and then investigate it. To introduce damped harmonic motion, we are essentially going to update our simple harmonic motion case to allow for damping. And we will do this by assuming that there is a damping force directly proportional to the velocity of the object, only opposite in direction. So the faster the object is moving, the bigger the force. And this is something that is often true, though not always, or at least approximately true for frictional forces. Now compare this force to the spring force and see the similarities. That force is directly proportional, but to the displacement of the object from equilibrium, and also opposite in direction to that displacement. So the definition is similar. Now we'll denote the constant of proportionality by B, which when using SI units is Newton per meter per second. So for every meter per second that the object is moving, there is 1 Newton damping force. So similar to the spring force where we used K as the constant of proportionality, that had Newton per meter units, which means for every 1 meter displacement from equilibrium, there is a 1 Newton spring force. Now, as you have already seen, a simple block spring system such as this is a nice way to find simple harmonic motion. You pull it back and you've got this nice oscillating motion. Moreover, we can tell what this motion is going to be like if we know what K and M is, the physical constants. For example, if I were to increase K, then refer back to the angular frequency term, that omega equal to square root of K over M. The fact that K is larger will now increase the angular frequency, which will make the oscillations faster. More intuitively, we can also make sense of it. The larger K is, the more stiff the spring is. Okay, so we should expect to see faster oscillations, which we do. And similarly, if I were to make M larger, then that omega term will become smaller, the angular frequency will become less, and the oscillations will be slower again. So we can tell a great deal about what the animation, the simple harmonic motion, will be like if we know what the physical constants K and M are. Now we're going to move to the damping case. Now there's a third constant, a damping constant, and illustrated here through this little sideways piston. Now we don't know how its value is going to affect the motion, so let's check. I've made it 200. Okay, it just kind of goes back to position. How about if we make it 20? And now it oscillates a little bit, but still dies down. Okay, now this is what we want to be able to understand. Just like in the simple harmonic motion case, knowledge of the physical constants K and M allows us to make some predictions about the motion, how fast it's going to be. Now we want to be able to do the same here for the damping case, but where there are three constants. We want to know how, knowing what K, M, and B is, can we predict what the motion will be when there's a damping force present. Take note that the little sideways piston, the origin of the damping force in the previous animation, is something like this, a little dashpot or a dashpot damper, a little piston. And you can imagine the faster you try to pull this piston out or push it back in, the bigger of a resisting force you're going to get. And it's these kind of piston, these kind of dashpot dampers that can be found inside shock absorbers. You still have your normal spring, but you have a little damper dashpot inside. And we'll be able to see by the end of today's lecture precisely why that is the case and how they should be calibrated. Okay, and now we will also most often use or view these kind of dashpots as the origin of the damping force in our diagrams and animations, though of course by no means are they the only origins of a damping force. Now let us look at the damping case more closely. Let's set up our diagram, indicate our forces, and use Newton 2. So exact same story to what you're used to, the only difference is that there's now an additional force. And based on our initial assumption, it's defined in this way, proportional to the velocity, just opposite in direction, which is the reason for the minus sign. And then, as before, everything in the same direction, x direction, we get this differential equation, which you'll notice is very similar to the simple harmonic motion case, except we've got this additional term, which is what I meant by when I said that we are going to be updating the simple harmonic motion case. So we've got to solve this equation, this differential equation. Now, how are we going to go about it? Before we do anything, we're going to have a little chat with our future selves, and we're going to learn that they are telling us that to make things a little bit easier on ourselves, let's rewrite one in a slightly different form. It is not mathematically necessary to do this. They just assure us that the notation will work out simpler if we do. So let's go ahead and follow their advice. So omega is equal to square root of k over m, and p is b over 2n. If I use that to rewrite 1, I get this. So see that you get this as well. I just divided by m on both sides and used these two definitions. Again, not mathematically necessary. It will just make life easier for us. And take note that omega is again the angular frequency, but not of the motion that we are seeing, but of the associated simple harmonic motion. So the motion we would be looking at if b was 0, in other words, if the damping force wasn't present. Okay, so how do we proceed? We proceed by realizing that we are in the context of differential equations. And in differential equations, there is a wealth of theorems and knowledge and techniques and recipes to fall back on. Here is a powerful one that tells you how you can find the general solution of an nth order homogeneous linear differential equation. We, however, have only got the second order one that we're trying to solve. So here is this powerful theorem in this second order case. It tells you if you've got a differential equation of this form and these coefficients are continuous functions, which in our case they trivially are because in our case they're constants, then if you can find two linearly independent solutions, in other words, two solutions which are not simply multiples of each other, then their arbitrary sum, c1 times 1 plus c2 times the other, where the c1 and c2 are constants, that is the general solution. So this is all that we've got to do. We've got to find two solutions that aren't simply multiples of each other. If we can do that, we can write down the general solution. And how are we going to find them? We're going to find them by also noticing, as I just mentioned, that these coefficients are constant. So this is a second order linear differential equation that is homogeneous with constant coefficients. And if you look up differential equation textbook, it will tell you that in that case, a technique or a recipe you can use is to substitute e to the lambda t into it. You're then going to get a polynomial in terms of lambda, which by the fundamental theorem of algebra, you will always be able to find two solutions in this case, or n solution if it's an nth order differential equation. So go and see what happens if you substitute e to the lambda t in there. For example, this term will be lambda squared e to the lambda t. And you cannot be able to write it in this form by dividing e to the lambda t on both sides. E to the lambda t, of course, is nowhere 0, so you're allowed to do that. So go and check that you do get this polynomial. Okay, so again, what does this now mean? It means that if you're going to find a lambda that satisfies this, then e to the lambda t is a solution of this. So as long as I can find two lambdas, I can find two of these functions, and they're not going to be linearly dependent, so I can then find the general solution. And how do we solve this? Well, this is just a basic quadratic formula that you're used to from high school. I've got the simple formula for it. Unfortunately, this could be negative in here, or it could be 0, so there are different cases to consider, and we will now go through each of them. The cases corresponding to if this term inside is positive, negative, or 0. And remember, through all that we're going to be doing from now on to solve it, in each case our mission will be to find only two linearly independent solutions. Right, so the first case, the simplest one, the one in which the term inside the square root is positive. If p squared is greater than omega squared, or equivalently, and go and see if you can see why it is equivalent. It's easy, but go and check beta squared greater than 4km. One or the other means the same thing. In that case, my polynomial has got two distinct real roots given by these two terms, plus the one square root and the other one minus that square root term. And please note that because p squared is greater than omega squared, you can deduce from this that this square root is less than p. So this term will be negative. And this one will obviously be negative. So lambda 1 and lambda 2 will necessarily be negative real numbers. So thus I've got those two solutions, and they are therefore, since lambda 1 and lambda 2 are different, these two functions are not multiples of each other, so they are linearly independent as I want. So because they're both solutions and they're linearly independent, the general solution is of this form, which is great. I've now completely solved that original differential equation for the case that p squared is greater than omega squared, or p squared is greater than 4km. Now, what does this case correspond to? Well, you can think about it. Lambda 1 and lambda 2 are both negative, so that means regardless what a and b is, the function x will return to 0. Might do it in a funny way depending on a and b, but it will do so without oscillations because this function does not, neither of these two functions oscillate. Not in the real case in any case. So this is what we call overdamping. And this is what happens when the damping force is strong. The damping coefficient is large enough. The system simply slowly returns to equilibrium. So as can be checked here. So go and check for this km and b value that in fact b squared is greater than 4km, or equivalently p squared is greater than omega squared. So go and do that check. So in this case, what's going to happen? It'll just look like this, slowly returning to equilibrium. And if you increase the strength of the damping constant, damping force, to here to 600, it'll just do so more slowly. So this is the simplest case. The damping force is too strong, you have a slow return to equilibrium without much of any other kind of interesting behavior. Now for the second case, let's look at what happens when that square root term falls away. If p squared is equal to omega squared, or equivalently b squared is equal to 4km. In this case, I only have that one root, lambda equal to minus b. So e to the lambda t with lambda equal to minus b, that is the only immediate solution that I have. So what am I supposed to do now? I'm after two solutions. Well, we consult the differential equation theory textbooks and look up this technique that we're currently using. And you will see that it suggests there, when this happens, try t e to the minus bt. And go and check, substitute it and see that this is also a solution. So great, I've got two linearly independent solutions. I mean, this one is not merely a multiple of that one. So the general solution is of that form. So great, that means there are two cases now that I've got the complete solutions for. And what does this correspond to? In this case, the damping force is just strong enough to damp out any oscillations. And we say that the system is critically damped. It means that the system very quickly returns to equilibrium when disturbed. So it's going to be the case here. So there you are, given k, m, and b. Go and check that p squared is equal to 4km or p squared is equal to omega squared, which means that this is a critically damped case. Now let's see what it looks like. It looks very similar to the previous case. But what's different here is it's much quicker back to equilibrium, which we will see a little bit better towards the end when we view these animations next to each other. And now we get to the final case, which is slightly more involved. What happens if that term inside the square root is negative? If p squared is less than omega squared, or equivalently b squared is less than 4km. Now I have two complex roots, lambda 1 and lambda 2, which, because this term is negative, means that lambda 1 works out to a complex number. So I can write it this way. And from year to year is the same as saying square root of minus 4 is I times the square root of 4. And let's call that square root term omega prime. Good. So that means I've got two complex solutions. Now we have to dip our toes a little bit into complex number theory. Okay, but we are after two real solutions. So let's not give up. Let's see if we can find it. Find them even though we've only gotten two complex solutions at this stage. Let's consider e to the lambda 1 t. So e to the minus p plus I omega prime t. So the complex exponential function, which is quite an extraordinary function. So normal exponent laws tells me I get e to minus pt, e to the, and then this term. And now, because of what is arguably the most extraordinary formula in mathematics, this we can write as cosine omega prime t plus I sine omega prime t due to the infamous Euler formula. I can rearrange it and get a real part and an imaginary part. Okay, and now how do we proceed from here? What we do now is to realize that we are dealing with a linear differential equation, and it is an homogeneous one. It's a fact that has helped us a lot up till this point. It's a very nice kind of differential equation in as much as finding solutions. And when I've got a real and an imaginary part to a solution like this, and it is a linear homogeneous differential equation, then you can go ahead and check one or two or three steps. That means that the real imaginary parts individually have to be solutions. So the green and the red part are both solutions. So that means I have actually found two real solutions that are clearly linearly independent. So that means that I can write the general solution as the sum of those two. And let's take out e to the minus pt as a common term and get that expression. And that we can rewrite using the cosine addition formula in this form. This is something that, strictly speaking, we did in the simple harmonic motion case as well. And go and check this if you want a good idea of what happened there. In the simple harmonic motion differential equation, the simplest way to find the solution is by noting that cosine omega, well, omega, not omega prime in the simple harmonic case, cos of omega t and sine of omega t are both solutions to that simple harmonic motion differential equation, which means that a times 1 plus b times the other is a general solution. So we just didn't write it. We immediately wrote it in this form with a single cosine. But effectively the same thing happened there. This expression you can write like this. And it's a good exercise for you to go and see if you can figure out how to do that with a cosine addition formula. Good. So what is this? This is what is called under or lightly damped and yields oscillations just with decreasing amplitudes. As you can clearly see here, I've got my cosine term, which means oscillations, but it's inside the e to the minus pt term, with p of course positive. So it's oscillations, but due to this term, it is reducing, oscillations of reducing amplitude. So for example, like this. So go and check for that k, m, and b value that it corresponds to underdamping, so that b squared is less than 4km. And if you run animation, you see a nice oscillating behavior. That is the cosine function inside of that e to the minus pt function. Okay, and depending on what kind of system this is, this may or may not be a good thing. For example, for a car, it is not a good thing. So here is underdamping displayed for a car. See, shocks should not do that. So you can do tests, so or sit down on a car and get off, and then if it hops up and down like that, then it is underdamping and the shocks need to be replaced. And now to end the lecture, let's look at all of these animations together. Notice two things. First, how much quicker the critically damped case returns to equilibrium, which is one of its hallmarks, and depending on your system, that may or may not be highly desirable. And the second thing to look out for or to notice is that the simple harmonic and the underdamped case don't have exactly the same oscillating frequency. That is because the one's angular frequency is given by omega and the other one by omega prime. Okay, and that's it for the first lecture on damped harmonic motion.